Hello, my name is Kelsey. I am going to be talking about the applications of DFT in material science. So DFT can be used to better understand measurable properties, which makes it a very valuable tool. Interesting materials properties are attributed to defects, and I'll touch on two examples on how we use DFT to approach understanding defect phenomena in material science. So a perfect crystal doesn't exist, and that's actually really great because point defects make materials very interesting. And so the few point defects I'm going to touch on today are vacancies, which is the absence of an atom from its site, substitutions, which is a foreign atom on an atomic site, and interstitials, which is an atom that's on site that's kind of crammed into a lattice. And these all influence the material's properties. That includes electronic properties, which might be the conductivity, optoelectronic properties, and thermodynamic properties. One really interesting case in material science and how point defects make materials very interesting are rubies, because the trace amounts of chromium in aluminum oxide introduce defect states which cause it to absorb certain wavelengths of light. So this is what makes rubies red. And there are also many other cases where point defects introduce defect states that create properties that we might not see, but influences the performance of certain materials. And this is why we're really interested in getting into these using density functional theory, because we can target point defects individually. So when we're looking at a certain material and wondering which point defects might influence it, we're mostly interested in calculating the formation energies. And it's done with this equation. And to demonstrate, we're just going to consider this arbitrary compound, AB. So we want to calculate the defect energies of this compound with a vacancy of A. So we're going to remove an A atom and calculate the DFT energy of that versus the DFT energy of the pristine lattice, so no node vacancies. So we plug these energies into our equation. We also plug in the number of defects times its chemical potential, which we can do by removing an atom and putting it in a reservoir and calculating the energy in its state, which should be in vacuum or in bulk. And we also take into account electronic properties. So the defect site might have a charge. We want to include the valence band maximum, the Fermi energy, and this electrostatic potential term, which accounts for any charge that may extend past the periodic boundary. So another thing that we're very interested in, and when we calculate formation energies, using DFT is to extend it to whichever environment we're interested in. And we do that through the chemical potential. And we can extend our DFT energies to whatever environment we're interested in using thermochemical tables such as the JANF tables. And this allows us to see how our formation energy plots may shift with the change in environment. It's a very valuable tool, and we also use it in other areas in density functional theory and not just in point defects. Which brings me to our next defect that I'm going to talk about. So instead of thinking of a defect that exists at a single point, consider a 2D defect or a surface. These are computationally expensive due to lack of symmetry in the system, as a vacuum region slows computational time. And I'll show that in the next slide. So this is what a typical surface energy calculation may look like, where you have this slab of a certain material and this vacuum region. And what's really important is that this surface doesn't interact with this surface through the slab or through the vacuum region, as since it's these are extended into infinity and tiled out into infinity, this surface may see their surface across the vacuum region. So it's important to keep in mind. So to calculate the surface energy, we calculate the DFT energy of this slab minus the number of atoms in the slab times its energy per atom. And we divide that by 2 times the surface area, as there are 2 surfaces in this cell. Something to keep in mind, though, is that ideal terminations of surfaces are not typical, and surface reconstructions which may form are hard to predict. and these may include atomic rearrangement or adsorption of foreign atomic species. So these should be kept in mind when using DFT as a means to calculate surface properties. Thank you for listening. I encourage you to look up the many capabilities of density functional theory in literature if you're interested. Have a good day.